Hello everyone, so I'm Guillaume Barré, so I'm research associate in Université Laval. I'm working with Christelle Laflamme, and I was in charge to install the new laser ablation ICP-MS system in Laval, and now I'm running it. And I will do a quick update about that at the end of my talk. But in the meantime, I did with Christelle a project on the VMS deposit, so it's what I will discuss right now. So just the aim of the project initially, we started with a simple fact, is that seawater sulfate is a huge sulfur reservoir that can interact with a lot of our deposits. But in the Archean, there is a problem that, as you probably know, the isotopic nature of sulfates through times evolved in the seawater, but there is a big lack of between 2.6 to 2.6 billion years to 3.2 without any evaporatic records, so we cannot track easily this isotopic signature of the seawater. So the question was how to track this isotopic signature. And it's really, as I said, it's really important because it's a big reservoir, and it can help to have ideas on the surface conditions in the Archean. But here we'll focus also on the signature to know the influence of seawater in our deposits in the Archean, basically. So there is no evaporatic records in the Archean, so we went to VMS deposit because, as you probably know, when you form VMS deposits, the seawater infiltrates the crust, so you altered the crust. There is a process of serpentinization, so you release H2, and thanks to the heat of an hydrothermal zone, you will be able to reduce the sulfates from the seawater into H2S through the process, the thermochemical sulfate reduction process. So this H2S generated directly from the seawater sulfate will be mixed with the H2S directly from the magma or from the leaching of the basaltic sulfides. So whatever the isotopic signature will be the same if it comes directly from the magma or from the leaching of the sulfides from the crust. And then you will mix this H2S from the seawater and from the basaltic magmatic signature, and you will record in the VMS, the massive sulfide lenses, directly the mixing of the isotopic signature of these two end members. So based on that, we would like to track the isotopic signature of the seawater that is recorded in the VMS deposit. So for that, we needed really well-preserved VMS deposit. So we went in the Abitibi, so in the Noranda camp and the Matagami camp. So we sampled different VMS, but also exhalite, all dated at 2.7 billion years. It's really important that they have the similar age, so we can compare them. And basically, we sampled 3 different types of deposits. So the first type was we sampled the McLeod deep mine in the Matagami camp, which corresponds to a subseafloor replacement VMS deposit. So we sampled directly the massive sulfides. The second type was seafloor VMS deposits. I would say classical VMS deposit that precipitate directly on the seafloor. So we sampled the amulet, the VMS, moosehead, shoring, and some other crops in the Noranda camp. And the last types correspond to different exhalites. The exhalites, which are basically hydrothermal circulations in the crust, associated or not directly with VMS, but we targeted exhalites linked with pillow lavas to be sure that there was an interaction with the seawater. So just to see quickly the petrography, we can observe in all of these deposits we observe generally similar sulfides in each of the deposits. So it's a mix of pyrite, sphalerite, chalcopyrite, plus or minus pyrrhotite, and really rarely galena. But so in all of these deposits, there is different proportion of sulfides. Even in a single deposit, you can have different enrichment in sphalerite or chalcopyrite, etc. So it's kind of difficult to just use a petrography as vectoring to know if there is an influence of the seawater inside. So that's why we did sulfur isotopes, so multiple sulfur isotopes. The classical, I would say, the classical analysis of sulfur isotopes, it's the delta 34S, so it's basically the ratio of the 44 and the 33. But the multiple sulfur isotopes, with the multiple sulfur isotopes, we can analyze the 4 isotopes of sulfur. So you have also, we can have the delta 33 and delta 36S, which give a lot of other information. So you can have better understanding of the source, but also have an idea of the process. And just for you to understand, later I will talk about the capital 33S, which is basically a relationship, direct relationship between the delta 33 and the delta 34S. But in a diagram delta 34, delta 33, delta 34, you can see that all the values are aligned in what we call the mass-dependent line, and the cap 33S can track a variation from this line. So it's really interesting. It gives you more information. So just how to acquire the multiple sulfur isotopes. We did bulk analysis. So for that, there is 2 steps. The first steps correspond to a wet chemistry to extract the sulfur from the sulfides. So we did the sulfur extraction in Laval. So I built this extraction line so we can do this first step directly in Laval. And then the second step corresponds to a fluorination analysis, and I went in Paris at the Institut Physique du Globe de Paris to do this second step. So the results we had on the different VMS deposits we sampled. So here it just on the x-axis the delta 34S and the capital 43S in the y-axis. Here I just plotted the Archean basalt signature. So basically it's around 0 per mil, and here just an estimated value of the seawater. So I will show you later how I determine that. It's just for you to understand the data. So the first results are from the McLeod depend, so the subsea floor replacement VMS deposit. So we observed a typical magmatic signature. So it was expecting, because in a subsea floor replacement, VMS, we don't expect any large or really limited seawater sulfate influence. So it's a magmatic signature. And here are the results of the seafloor VMS from Noranda. So here you see that there is an enrichment in the delta 44S and a depletion in the cap 43S. So we start to see an influence of the seawater with a trend between the seawater and the magmatic signature, like that. So it's which is expected because we are at the seafloor, so we have the interaction directly with the seawater. Just a quick thing about the temperature determination. So with multiple sulfur isotopes, what is interesting is that we can determine if a mineral pair, so basically pyrite, pyrrhotite, are at isotopic equilibrium, and if so, you can determine the temperature of precipitation of these sulfides. So from all these pairs, we analyzed this. Here, there was just 4 pairs that are at isotopic equilibrium, and so we can determine the temperature of precipitation. So in Noranda, in Amulet and Mouzet, it's around a bit more than 300 degrees C, and around 250 degrees C in McLeod Deep. So the last results on the exhalites. So on the exhalites, there is two groups, I would say. So there is some exhalides that are enriched in the cap 43S, and some exhalides that are depleted in the cap 43S. So basically, there is different type of exhalite. So there is exhalite far from a VMS deposit and exhalite close to a VMS deposit. So just to show you to explain this isotopic signature, as you probably know, in the Noranda camp, most of the VMS deposits are aligned in what we call the main contact tooth. And when we observe the exhalides that show an influence of the seawater, so basically here it's exhalate with a really huge influence of the seawater sulfate, and here no influence. So the exhalate with seawater sulfate influence are also on the main contact tooth, when the other exhalides that not show any seawater sulfate influence are not on this main contact tooth. So it's really interesting. So it can be used as a vectoring tool to target VMS deposit. But to explain why there is this difference, all this difference, so just here a subsea floor replacement VMS deposit, so we don't expect any seawater sulfate influence. On a seafloor VMS, there is a mix of the magmatic and the seawater sulfate influence. And for the exhalides that are directly linked to VMS, so on the main contact tooth stratigraphic level, here you are close enough to the main hydrothermal zone, so the temperature is high enough to be able to reduce efficiently the seawater sulfate. So it's kind of a complete TSR here. So that's why you record, but there is no important magmatic influence because you are not directly in the main hydrothermal zone. So you record mainly the seawater sulfate influence in this exhalite. When for exhalites that are far from a VMS or disconnected from a VMS deposit, the temperature is lower, so the TSR is less effective, and so you record magmatic or sedimentary, even possibly biological signature in the sulfur isotopes on this exhalite. So here it's just to explain the data we have, and so from this data then the idea was to determine the isotopic signature of the seawater sulfate directly. So for that we can use a two-component mixing model. So basically the isotopic signature of the VMS deposit corresponds just to the addition of different proportion of the basaltic signature and the seawater sulfate signature. So here we just have to change this equation just we want the isotopic signature of the seawater sulfate. The only missing part is we just need to know the percentage of sulfates which can be incorporated into the VMS. So for that, to have an idea of this proportion, I did a compilation of data from the literature on different VMS of different age to see the variation of the proportion of the seawater sulfate in the VMS deposit. And as you can see here, there is a huge variations through times, but general trend that from modern time to the Archean, there is a decrease of the percentage of seawater sulfate incorporation in a VMS deposit. And there was already just one estimation from Kidd Creek, the VMS of the incorporation of the sulfates around 17%. So let's keep that in mind. So it would be an idea of the percentage, the proportion we can use for our seawater sulfates isotopic signature determination. So let's go back to this equation, so the two-component mixing model. And so basically what I did is just I changed this proportion of seawater sulfate to determine the isotopic signature of the seawater sulfate. So here I changed from 30% to 5%. And here we can already discard some value, because we know that here are our value on exhalite. So we know that there is a huge influence of seawater here. So all these proportions that cannot explain the most depleted value cannot be the right value for the seawater sulfate. And similarly, for example, this 5% incorporation of seawater sulfate, we get value which is higher than the modern seawater sulfate isotopic signature. So it's highly improbable that it could be the right isotopic signature. So the most plausible values are between 20 and 10% of seawater sulfate incorporation in the seawater, but we still need a bit more constraint to determine the right value. So for that, I compiled different isotopic signature from other VMS deposits in the world. So there is not a lot of multiple sulfur isotopes value in the literature, but there is other value on the Noranda camp, on the Kidd Creek VMS, La Ronde as well, but there is also some value on the Teutonic Bore, so it's a VMS in the Yilgard craton. And what is really interesting that we observe really similar isotopic signature between the VMS, all these VMS deposits dated at 2.7 billion years. But also there is, in Teutonic Bore, they analyze what they call the interpilobasalt, which basically corresponds to exhalite. So, and we see that we have really, really similar isotopic signature between our exhalite and the interpilobasalt they analyzed. So it implies that there are these extraordinarily similar values between the Abitibi, Kidd Creek, and the Yilgard craton. It shows that the isotopic signature of sulfate in the ocean at 2.7 billion years was homogeneous. So it's really interesting, and so just with that, it's a big clue, because most or some persons thought that there was different isotopic signature. But anyway, just go back to determine the exact isotopic signature of the sulfate, oceanic sulfate. So we have this variation of proportion, so we can discard all of this value because we cannot explain the isotopic signature of the interpilos and the exhalite signature. And the 10% is a bit far from that. And so the most probable proportion are between 17 and 15%. But here, the problem that the 17% already proposed at Kidd Creek cannot explain all the isotopic signature in the interpilos. So the most probable proportion of seawater sulfate incorporation is 15%. So it leads to an isotopic signature of the seawater sulfates in the Archean at delta 34S at 9 per mil, around 9 per mil, and a cap 33S around a -1 per mil. So thanks to that, we can just add a value, a real value in this diagram in the delta 34S and cap 33S. So like that, we have an N member for the isotopic signature of the seawater sulfate. And with this N member, we can track the influence of seawater in our deposits, for example. So yeah, it's to conclude on this VMS part, and now I will just finish with the ICP-MS we developed, we installed in the university level. So we installed, it was fully installed on October 2021. So it's a laser ablation system with a triple quadruple ICP-MS. And so far, we run it routinely trace elements on silicates and sulfides. We can do maps, for example. Here it's an example of a garnet maps we did with Antoine Godet. So just to show you that our ICP works pretty well. But what I really want to show you is that we are, with Crystal, we are developing sulfur isotopes in situ with this laser ablation system. So I will show you some preliminary results on that. So basically, we can, I use the same the scene sections of the VMS deposit I just show you some results before. So I know the isotopic signature. I have an idea of the isotopic signature of this VMS and exalite samples. So here, what we can do so far with sulfur isotope with the laser, we can do lines. So here there is different lines on pyrite and pyrrhotite. So far we can analyze just pyrite and pyrrhotite because we just have standards for pyrite and pyrrhotite. We have one standard for chalcopyrite, but we need another one to be to have a secondary standard. And so for each line we can determine the isotopic signature. So it's an in situ technique. So yeah, you have the isotopic signature where you analyze basically. And so it's really interesting because we can see the variation within grain, etc. So far, the error on the delta 44S is relatively big at 1.5 per mil, but we just have to increase the stability and the accuracy of our result, but I'm pretty confident that we'd arrive to decrease this error. So just to show you some really preliminary results. So here are the results on 8 different scene sections from the VMS deposits of Noranda and Matagami. So you see that here I just have really huge errors, but I'm pretty, we have to better determine these errors, but I preferred to add huge errors than to show you too small errors. And anyway, even with these big errors, we can see that we arrived to see the difference between, for example, exalites and subsea floor replacement VMS. Here, it's just the circles correspond to pyrite, and this kind of square correspond to this diamond correspond to pyrrhotite. And here you can see that there is a difference between the pyrite and the pyrrhotite isotopic signature. And when you do the average of the two, you get a similar isotopic signature than the one we get by bulk, and which makes sense because by bulk you have the isotopic signature of both the pyrite and pyrrhotite. So it's really interesting. So it means that we have the precision to determine the isotopic, to differentiate the isotopic signature between two phases with the laser ablation technique. So just the ongoing challenges. So as I said, we'll try to reduce the error on each value, and I'm pretty confident that we can decrease it. We'll see how much, but definitely less than 1 per mil. So far we can do just lines, but we worked to be able to do spots as well, so like that will be better targets, like the zoning inside a single grain. And the last part, we will try to do multiple sulfur isotopes, not only the delta 44, but also the delta 43S in situ, which will be really interesting. So far, you can just do multiple sulfur isotopes just by SIMS, but it takes time, and the sample preparation is really, really important. So with the laser ablation, you can directly analyze in a scene section, which will be way faster than SIMS and way easier to do. So if you have any question, I'm here for you.
Okay, we have time for a question or two. Mark?
No.
I didn't hear anything about metamorphism. What is this doing with such such good precision? Can you pick those?
For the laser ablation, you mean?
Yeah.
Oh, the metamorphism. Well, here we used these VMS deposits mostly because the metamorphism is really low, the deformation as well. So, I mean, the metamorphism can change the isotopic signature within different generation of grains. So, if we arrive to see the variation within a grain, it means that we can observe the metamorphism. So, it just depends. I'm not sure. Definitely, the metamorphism itself will not affect the measurement. It will affect the isotopic signature of what we will analyze. But so, yeah, I don't see any problem if we analyze metamorphic rocks, for example. Yeah.
Can you use one standard for all your sulfides, or do you have to matrix match for the different ones?
No, we use a matrix match so far because some previous studies show that it's better to use matrix match, but we didn't try yet to use one isotopic reference material. But definitely it will be something we will try to do. But so far we prefer to work with matrix match. So we have for matrix match reference material for pyrite, pyrrhotite, one for chalcopyrite, and we'll probably arrive to get one for arsenopyrite also. And we'll see if we can use just one standard for everything. Yeah. Yes.
I didn't quite understand why the exalites near the VMS deposits would show more of the seawater signature than the deposits themselves, because the fluids are all coming out of the same vent.
Yeah, I think it's just because near to the VMS you have way more influence of the magmatic fluids, even if it's directly from the magma or just for the leaching of the crust. Just the exhalites, I think it's something I still have to work a bit on, but I'm pretty sure that it's just that there is less influence of magmatic sulfides, because you are not directly, you are related to the hydrothermal zone, but I think you are a bit far from this hydrothermal zone compared to the VMS itself, so there is less influence of that. So I think it's that, but it would be interesting to discuss about that, because it's just an idea, but if you have other idea of that, it would be interesting to discuss.
Yeah, these exalites aren't entirely straightforward. Right? They could form
Yeah.
the question is, how do they form exactly?
Yeah.
It seems to suggest they're not just slightly more distal expression of the same.
Yeah, definitely. Yeah. As nobody is really clear on how they form, it's a bit difficult to say. But definitely there is a link of where they form, because just the exalites that show the isotopic signature of the seawater sulfates are all linked to the main contact tooth, as all VMS, but all the others are definitely not linked to this contact. So definitely there is a genetic link on the isotopic composition, but it will be interesting to better understand how they form all of them. Yeah, definitely.
Okay, thanks. I think we'll move on.
Okay.